Part 1 is Lewis electron dot structures. You are going to draw the Lewis or electron dot structures of the following atoms. So please refer to page 3 of the handout. The atoms are hydrogen, carbon, and oxygen. Under Lewis dot structure, you are going to first write the symbol of the atom. So for number 1, you are going to write H. The Lewis dot structure is dependent on the number of valence electrons in the atom. For hydrogen, you have 1. Therefore, you are going to write 1 dot. Since you only have 1 dot, therefore, the number of single covalent bonds that H can form is 1. Therefore, covalency is 1. For carbon, the symbol is C. So you are going to write C under that Lewis dot structure. And because you have 4 valence electrons in carbon, you are going to write 4 dots. 1 dot on each side of the carbon. You have 4 sides. You are going to write 1 dot above, to the right, below, and to the left. And because you have 4 unpaired electrons, the covalency of carbon is 4. Because the number of single covalent bonds that carbon can form, the total will be 4. Therefore, covalency is 4. Third example is oxygen. The symbol is O. You are going to write under Lewis dot structure the symbol O. And because oxygen has 6 valence electrons and oxygen has 4 sides, you are going to write 2 dots on one side. Next side is going to be 2 dots again. The third side, 1 dot, and then the last side or the fourth side is going to be 1 dot. You have 2 unpaired dots or 2 unpaired electrons in oxygen. Therefore, the covalency is 2. Next set of atoms are nitrogen, fluorine, and sulfur. In the Lewis dot structure for nitrogen, you are going to write first the symbol for nitrogen, which is N. And the number of valence electrons in N is 5. Therefore, on one side, you are going to write 2 dots paired up, and then the second side, 1 dot, third side, 1 dot, and then the fourth side, 1 dot. Therefore, you will have 3 dots not paired up. Therefore, the covalency will be 3. Next example, fluorine. You will have the symbol F, and fluorine has 7 electrons, 7 valence electrons. Therefore, you are going to distribute 7 electrons on the 4 sides. So one side will have 2 dots, the other side 2 dots again, and then the third side another 2 dots, and then the fourth side only 1 dot unpaired. Therefore, the covalency will be 1. It's the same as hydrogen because hydrogen will only form 1 bond. The same thing as fluorine. 1 bond, therefore covalency is 1. Next example will be sulfur. So sulfur, symbol is S. So you are going to write S in that blank under Lewis dot structure. But because sulfur will behave like oxygen, therefore refer back to the previous page or previous slide about sulfur because it's like oxygen. In this page, part 1, Lewis electron dot structures, we are going to draw the structures for the molecules instead of atoms. So please refer to page 4 of the handout. Examples in this page are CH4, NH3, H2O, and HF. Total valence electrons would be the sum of the valence electrons of all the atoms in the molecule. So for number 1, CH4, carbon has 4 valence electrons plus 4 times 1 because H has 1 valence electron. So refer to the bottom number of valence electrons. H is 1, carbon is 4, N is 5, oxygen is 6, fluorine is 7. So go back to CH4 number 1. Lewis dot structure, you will write a central atom which is carbon. So you will have 4 dots around the 4 sides of carbon. Instead of a dot, you will make a line. So you will have 4 lines around carbon, and then at the end of the line, you will write H's. So you will have 4 H's around carbon. Number 2, NH3. Total valence electrons would be 5 for nitrogen plus 3 times 1 would be 8. Lewis dot structure for NH3, you will have a central atom which is N. You will have 5 dots. So 2 dots above paired up, and then the 3 dots on the 3 sides would be unpaired. So instead of a dot, the 3 dots make a line. So you will make a line. At the end of these 3 lines, you will put H's. So you will have 3 H's around N, and then 1 lone pair above the N. Number 3 example is water, H2O. Total valence electrons would be 2 times 1 plus 6 would be 8 again. Lewis dot structure, you will write O first. You will have 6 dots, 2 paired up. So 1 lone pair above and then 1 lone pair below. So 2 dots above, 2 dots below. And then on the other side, on the right side and left side, you will have 2 dots unpaired. So instead of unpaired electron or unpaired dot, you will make a line. So at the end of each line, you will make, or you will write H. So you will have 2 H's on each of the line. Last example in this page or in this slide is HF. So HF, you will connect H to F for the Lewis dot structure, but for the total valence electrons, you will have 1 plus 7 because you will have 7 valence electrons in F. So Lewis dot structure, connect H to F, make a line. However, for the F, you will have 6 more dots. So pair up 1 dot, so you will have a lone pair. Okay, so you will have 3 lone pairs or 3 non-bonded pairs on F. Now in this page, we have again 4 examples. The first one, H2S, okay, it will be the same as water, H2O, so refer back to the previous slide. CHCl3, all right, total valence electrons will be 4 plus 1 plus 3 times 7. The Lewis dot structures will be similar to the CH4 number 1 example in the previous slide. However, you're gonna put the you call it the lone pairs or non-bonded pairs or 2 dots on the Cl. So you will have a lot of electrons on the Cl because they're not bonded. So in one Cl, in each Cl, you will have 6 electrons non-bonded. So meaning that you are gonna write it as 2 dots on one side of chlorine, 2 dots on one side of chlorine, and another 2 dots on one side of chlorine. And you will do the same thing for the rest of the chlorines because you will have 3. Next example is C2H4. So this one, don't connect the H's together, okay? You will start connecting the C's together. But let's go back and calculate the total valence electrons. So you have 2 carbons, so 2 times 4 plus 4 times 1. Okay, so add together. The Lewis dot structures, you start connecting the C's together. And then remember that the carbon should have 4 lines. So if you're missing electrons on the carbon, make multiple bonds, okay, for this C2H4. In this case, you will have a double bond on the carbon to carbon double bond, and then distribute the H's on each side. The molecule is symmetrical for the Lewis dot structures. Now, next example in this page is C2H2. Total valence electrons will be 2 times 4 plus 2 times 1. Now, if you look at number 7, basically we took out two H's because we now have only C2H2 for number 8. However, for 7, we have C2H4. Therefore, you're going to have another multiple bond. You will have a triple bond instead of a double bond. So Lewis dot structures, you will have carbon to carbon triple bond, and then the two H's on each side of the carbon. It will be symmetrical molecule. Okay, now the last two examples in this page. So the same idea, instead, however, we have sulfur in number 10. However, CO2 and CS2 are actually similar or the same in terms of counting the total valence electrons. So when you do CO2 is the same as CS2. So let's do CO2, that's carbon dioxide. Carbon will have 4 plus 2 times 6, that's total valence electrons, exactly the same as CS2. Lewis dot structures for both are the same, except that for CS2 you have S instead of O. So again, you have a central atom, which is a carbon. So write oxygen on both sides of the carbon, but because carbon needs 4 lines, okay, you have to pair up everything. So therefore, you will have 2 double bonds on the carbon so that you have 4 lines on the carbon, and then another double bond to the oxygen. All right, the molecule is symmetrical. However, for oxygen, you will have 2 lone pairs on each, the same thing as sulfur for number 10. So we're done with page 4 of the handout. We are now going to do part 2, which is going to be molecular shapes. So page 5 of the handout. So in fact, all of these are linked together because I'm using the same example. So first example again is CH4. So what is an arrangement of regions? This refers to the maximum angular arrangement of bonded and non-bonded electron pairs in the atom, in the central atom. And then lone pairs are referred to as the non-bonded electrons or dots that you did not form a line. The molecular shape will be dependent on the central atom, and then it's going to be dependent on the bonded electron pairs. So there's going to be 3 types of molecular shapes in this page, and those are tetrahedral, trigonal pyramidal, like a pyramid, or bent. So it's going to be bent or trigonal pyramidal, the shape, because of the lone pairs coming from VSEPR or Vesper theory. That's valence shell electron pair repulsion theory. So let's do CH4. So arrangement of regions, the maximum angle that C to H will form around that, and that the H's will form around the carbon will be 109.5. It's not 90 degrees. So therefore, for this case, the arrangement of regions will be tetrahedral. Tetrahedral, you will have 4. Okay, either it's going to be bonded or non-bonded. Okay, so if you write the Lewis structure for CH4, okay, you will have 4 lines around the carbon, and then it's going to be bonded to 4 H's. You will not have any lone pairs, therefore 0 lone pairs. Molecular shape, right, is going to be dependent on that VSEPR theory. So because you have 4 bonds, the shape will be the same as the arrangement of regions because you don't have lone pairs. Therefore, it's going to be tetrahedral. NH3, however, if you refer to your Lewis dot structures, you will have a lone pair, 1 lone pair on the end. The H will not have a lone pair. Therefore, you have 1 lone pairs. You have 1 set of lone pairs. You will have 1 pair of 2 dots. Therefore, the arrangement of regions is the same as above because you have 3 bonded pairs and 1 lone pair. Therefore, the arrangement of regions should have been tetrahedral. Therefore, the molecular shape is not tetrahedral because of the presence of lone pair. Therefore, it's going to be pyramidal or trigonal pyramidal. Water, the same thing as CH4 and NH3. You will have the arrangement of regions as 4, including the non-bonded pairs. You have 2 non-bonded electron pairs and you have 2 bonded pairs. Therefore, you have 4 arrangement of regions or tetrahedral. However, in this case, you have 2 lone pairs. So for NH3, you have 1 lone pair, and CH4, 0 lone pair. For water, you have 2 lone pairs. So if you look at just the lines, you will have only 2 lines. So basically, you're just forgetting the presence of the lone pairs to determine the molecular shape. The same thing as the NH3, even though you have a lone pair, you actually just ignore that and then you're just looking at the bonded pairs. It's like pyramidal shape. Water, you're just looking at the bonded pairs, therefore it's just going to be bent as the molecular shape. Next is HF. So arrangement of regions for HF is because it's just 2 atoms, you call it diatomic molecule. It's just going to be linear. So you're just connecting one line from H to F. So number of lone pairs will be based on the F. You will have 3 lone pairs because you have 6 dots and they're paired up. Therefore, it's going to be 3 lone pairs. Molecular shape, the same thing as the arrangement of regions. It's going to be just linear. So H2S is the same as water, so refer back to the previous slide. Now, CHCl3, arrangement of regions is the same as CH4 in the previous slide, number 1 example. The number of lone pairs will be just on the chlorine, okay? You will have 3 lone pairs in each chlorine, but because you have 3, okay, so 3 times 3 will be 9 lone pairs. Molecular shape is the same as number 1, CH4, because it's based on the central atom, in this case, carbon. So for the Lewis dot structure, don't connect the Cl's together in this example, which is number 6. So next, page 5 of the handout, again at the bottom. So we're still doing molecular shapes. So C2H4, arrangement of the regions, all right, it's going to be just planar. So there are no lone pairs on the carbon, all right. Molecular shape is the same because you don't have any lone pairs. Nothing is deviating from that maximum arrangement of the bonded electron pairs. Therefore, arrangement of regions and molecular shape for C2H4 is actually the same. It's going to be planar. So if you refer back again to the previous slide about C2H2, so we're just referring to just one carbon, the same thing as number 7, because the molecule is symmetrical anyway. So arrangement of regions is just going to be linear because it's on a line. You have a triple bond. No lone pairs. Molecular shape, just linear because there's no lone pairs or non-bonded pairs in the atom or the central atom, which is carbon. Therefore, molecular shape and arrangement of regions for 7 and 8 are the same. So the next example, CO2 and CS2, refer back to the previous page, actually for the Lewis dot structure, and it's just on a line. Therefore, arrangement of regions is linear. The same thing as CS2. CO2 and CS2 are the same. Lone pairs is going to be dependent on the dots that you put on the oxygen, not on the carbon, because there are no lone pairs, there are no dots, okay? Just lines. The same thing as CS2. So, behavior of CO2, or the way you determine arrangement of regions, the number of lone pairs, and molecular shape, CO2 and CS2 are the same. So last part of the handout or this experiment is about intermolecular forces of interaction. And then it's going to be page 6 of the handout, one page. So again, the same example. So you can also look at the Lewis structure and also the geometry. It's actually dependent on the geometry. And also the Lewis dot structure of the molecule. So you're going to mark accordingly if it's exhibiting H bonding, dipole-dipole, induced dipole, or polar nonpolar. So don't mark anything if it's not exhibiting any hydrogen bonding, nor dipole-dipole, nor induced dipole. And then the last column, you are going to write whether it's polar or non-polar. Okay? So let's read the bottom, the notes at the bottom. So H bonding is going to be exhibited by molecules with H2O, H2N, and HF bonds. Dipole-dipole, molecules with an oxygen bonded to a carbon or an H, and then, or to an N, or to an S, or to an F, a Cl, Br, or I. It can be single, double, or triple bonds. And then induced dipole exhibited by all molecules. Therefore, for the induced dipole, you will check or mark an X in this slide, the 3 examples. So now mark an X in your handout, induced dipole, for all of the 3 molecules in this page or in this slide. Okay, so now let's do H bonding. So the rule is for H bonding, this terminology is you are going to look for H2O, H2N, and HF bonds. Therefore, because there's no, for number 1, there's no O, N, or F, therefore CH4, no H bonding. Okay? Dipole-dipole, no, because carbon to H is actually not included in the list for the dipole-dipole. Therefore, for the CH4, you will only mark an X, induced dipole. Therefore, it's non-polar because they're really what is called a dipole moment. There's no difference in terms of the polarity for each of the C2H. It's considered a non-polar molecule, and the C2H bond is considered non-polar. Now, let's go to number 2 and H3. So, H bonding, yes, because there's H to N, so you're going to mark it with an X. Dipole-dipole, yes, because there's going to be H to N bond. So, you will check or mark on an X, H bonding, dipole-dipole, and induced dipole. So, is it polar, non-polar? So, look at the way the geometry is pyramidal, and because of the lone pair, it's not entirely symmetrical. Therefore, this molecule is polar. So water, the same thing as NH3, you will have everything checked. H bonding to induced dipole, and then it's also a polar molecule like NH3 because of the presence of the lone pairs. It's not entirely symmetrical. The pool of the polarity or electronegativity or the dipole moment is not the same for water because the way you write the molecular shape is not in a linear way or linear fashion. It's bent. Therefore, it's going to be a polar structure, polar molecule. Now, next group of examples, HF, H2S, CH, Cl3. So again, because all molecules exhibit induced dipole, you're going to mark with an X the third column, induced dipole, for all of these examples. So now let's go to H bonding. For HF, yes, because there's an HF bond. Dipole-dipole, yes. So for number 4, you will check all the 3 H bonding to induced dipole. Therefore, this is also polar because the molecule is not symmetrical. Fluorine is pulling the bond towards itself because it's attracting the electrons towards itself. Okay? So number 5, H2S, all right, refer back to water. It's the same. However, it's not entirely exhibiting H bonding because the H bonding is only exhibited by molecules with H2O, H2N, and HF. Therefore, you will not have H bonding for H2S. However, you will have dipole-dipole and induced dipole, and this molecule is also polar like water, H2O. Okay, number 6, CHCl3. Again, no H bonding because you don't have HO, HN, or HF. Dipole-dipole, yes, because you have chlorine. Okay? And then induced dipole, yes, right? So mark that with an X. Polar, yes, because the molecule is not symmetrical. If you have CCl4, it's going to be non-polar because the way the polarity or the way the molecule is arranged, with respect to the carbon, it's pulling or it's canceling the pull of one chlorine to the other side of the tetrahedron or the tetrahedral structure. Okay, the last set of examples, page 6 of the handout for part 3, intermolecular forces of interaction. Okay, so again, the intermolecular forces of interaction are the forces of interaction attracting the molecules together. So it's exhibited in terms of whether it's going to be a gas state at room temperature or liquid or a solid. But I mentioned this in the lecture, but for this example in the lab, we're just focusing on identifying whether the molecule will exhibit H bonding, dipole-dipole, induced dipole, and whether the molecule is going to be polar or non-polar. So now let's go to number 7, which is C2H4. And C2H4, if you refer back to that Lewis dot structure or the molecular shape, it's going to be planar. So for this one, this doesn't have any H bonding, therefore don't mark it. It will have, does it have a dipole-dipole? No, because the molecule actually doesn't have any O, N, S, F, C, L, B, R, or I. But again, all of the examples in this slide, 7, 8, 9, 10, will have induced dipoles. You will have to mark that with an X. Now, number 7, C2H4, is it polar or non-polar? No, it's not polar because the molecule is symmetrical and the carbon to H bond is not polar and the molecule is symmetrical, meaning that the pull of one side is the same as the pull of the other side. It's like a tug of war. If the weight of one side or the weight of the people pulling the rope is the same, you will not have, nobody wins. Or like if you have a seesaw, the weight is the same, you will not press one side of the seesaw or the tug of war thing of the, the pull of the rope. It's going to be the same. So you can think about it this way. So the molecule number 7 is non-polar. Now let's go to number 8. Again, no H bonding. This is similar to C2H4. Dipole-dipole, no. Induced dipole, yes. It's also non-polar because the effect of one side of the molecule to the other side is the same. The pull is the same. Now, so CO2 and CS2, this actually behave like your number 8. Okay? So it has some dipole-dipole, okay, because you have a CO bond and CS bond in number 10. You also have induced dipole, but the molecule as a whole is non-polar because of the fact that the pull of one side is the same as the pull of the other side. So it's a completely symmetrical molecule, therefore it's non-polar for number 9 and number 10. That is the end of this experiment, which is part 3. So all you need to do is you can re-listen to this presentation and then write the lab report, which is just filling up all the blanks in this report form for experiment 2.